In the last unit, we found relations that told us how different flow properties respond to a differential area change. But what does this mean physically? So let's examine what happens in both diverging and converging nozzles. From the last unit, we found these two really useful relations between the velocity change and the area change, and between the pressure change and the area change. So let's see what these tell us. First, about the diverging geometry when we have subsonic flow. So for subsonic flow, this term which is appearing in the denominators, 1 minus m squared, if the Mach number is less than 1, then this is going to be a positive quantity, so greater than 0. So if we're looking at the diverging case, where dA is greater than 0, the fact that this is positive means that the change in velocity, due to this negative sign, is going to have the opposite sign of the change in area. So this increasing area is going to cause a decreasing velocity. Correspondingly, this pressure relationship is telling us that that increasing area is causing an increase in pressure. These have the same sign. So this diverging area is acting as a subsonic diffuser, something that decreases velocity and increases pressure. Next, let's look at the case where we have a converging geometry. So dA has now changed signs, it's decreasing, so dA is negative. So we're going to have the opposite trends from what we observed here. So the velocity is going to increase and the pressure is going to decrease. So this converging geometry is a subsonic nozzle. So this is accelerating the flow in exactly the same way as when you place your thumb over the end of a hose, you're able to accelerate that flow of water out of the hose. Next, let's examine the supersonic case. So m is greater than 1. If m is greater than 1, that means that this term 1 minus m squared is going to be less than 0. So what that does is switch the trend of velocity with respect to area. So this term on the denominator is now negative, so that cancels with this negative sign. So that means when we have an increase in area, we're going to have an increase in velocity, and correspondingly a decrease in pressure. So this diverging area is acting as a supersonic nozzle, and that is exactly what we want to use on the end of a scramjet combustor, because a scramjet is a supersonic combustion ramjet. So we've got supersonic flow exiting the combustor, entering the nozzle, and we want to have one of these diverging nozzles to accelerate it and extract the maximum amount of thrust. Finally, if we look at the converging geometry, we're just going to have the opposite trends. So this is now going to act as a supersonic diffuser, which is decreasing the velocity and increasing the pressure. Now we have a picture of how flows behave in converging and diverging geometries. But why does the character of a flow change when we go from subsonic to supersonic speeds? Let's make use of equation 3 from the last unit. We can rearrange this to show that the Mach number is equal to the negative of the ratio between the density dilatation and the velocity dilatation. This means that for subsonic flows, the magnitude of the density dilatation is going to be less than the velocity dilatation. Therefore, keeping the mass flow rate constant when the area increases, for example, is achieved by a decrease in velocity. This expression also tells us that density and velocity always have the opposite trends, so that increase in area will also result in an increase in density. The decrease in velocity must be large enough to balance both these increases and keep the mass flow rate constant. The velocity dilatation is dominant for subsonic flows because, as we discussed at the start of this section of the course, it's very difficult to produce large density changes in low-speed flow. On the other hand, for a supersonic flow, large density changes can be induced, and the density dilatation dominates over the velocity dilatation. So, for example, an increase in area will be counterbalanced by a decrease in density. One interesting question that still remains from this discussion is what happens when the Mach number is exactly 1? We'll look at this in the next unit.